Hello and welcome to this fifth of six films about the kinetic theory. It's about vapor pressure and it's the last film that involves any new theory. The sixth film in this series just gets you to practice a few questions on this topic. Okay, so this film deals with vapor pressure. It explains why liquids exert a pressure, and hopefully by the end of it you'll be able to relate energy distribution curves to the fact that liquids evaporate at all sorts of temperatures, and you'll understand how the boiling of a liquid relates to the vapor pressure and how the vapor pressure of a liquid will depend on how pure it is and also on its temperature. Okay, now there's a lot to cover in this one, so we'll get straight on and try and get through it quite quickly. Remember, you can pause it anytime you like. Okay, so why do all liquids evaporate before they boil? Okay, so in other words, why will a puddle be here today but gone tomorrow, even though it never gets anywhere near 100 degrees centigrade? Well, let's look at these two, let's look at this one energy distribution curve and the two lines on it. Okay, so we've got a blue line at 15 degrees centigrade and we've got a red line at 20, and what this graph is showing is that the average energy at 20 is higher than the average energy at 15. We know that, okay? But what we also can see is that at both these temperatures, even though they're quite low, there are particles that have greater than this energy, okay? They have enough energy to escape from the liquid and evaporate. So they can overcome the forces of attraction, they can turn into a gas, okay? There's more of them at the high temperature than there is at the blue one, but regardless, okay, there are some particles that can do that. Okay, so even if the liquid isn't hot enough to boil, there are particles which can evaporate. Okay, now that's really important, because if I put a liquid in a sealed container, some of it will immediately start to evaporate, and you can see at the beginning here there aren't any gas particles above it, but they're evaporating, and eventually there'll be lots of gas particles up there that have evaporated, and some of those will reach the surface of the liquid and condense. Okay, liquid particles will continue to evaporate, but particles will also continue to condense, and when these two processes reach a balanced state, which only depends on the temperature, okay, so the rate of these two processes only depends on the temperature and the type of liquid that you've got, they'll reach a pressure which is limited by the two rates of these processes, okay, by the balance of them, all right, and we call that the equilibrium vapor pressure, okay. So in other words, there will be a certain pressure that any one particular liquid will exert above that liquid, called its vapor pressure, and the reason it occurs is because some of the liquid evaporates and eventually will reach a limit because the evaporation and condensation start to balance out. Okay? This vapor pressure depends on the temperature and the nature of the liquid, okay? Because the forces between particles will play a role, so the nature of the liquid is important, and how much energy the particles have, in other words how many can evaporate, will also play a role here. So the temperature is going to be important. Okay, we call this pressure above the liquid its vapor pressure, okay, and it depends on the temperature and the liquid itself. So here are a few graphs that show the vapor pressures of different liquids at different temperatures, and you can see if we look at water here that its vapor pressure is gradually rising as its temperature rises, and at 100 degrees centigrade it reaches this pressure, 1 atmosphere, or 760 torr. Okay, if I look at ethanol, let's say 60 degrees, I can see that its vapor pressure is higher than that of water, and when I get to 78 degrees it looks like the ethanol is starting to boil, and again its vapor pressure has reached 1 atmosphere. Okay, and if I look at diethyl ether here, which boils at 34.6 degrees, I can see that its vapor pressure is much higher than those other two liquids at any particular temperature. Okay, so the lower the boiling point of a liquid, the higher its vapor pressure at any particular temperature. Okay, and with all these liquids, the vapor pressure rises as the temperature rises. Moving on, what happens when a liquid actually boils? Okay, that last graph looked at boiling points, right? It showed that all those liquids boiled when their vapor pressure reached a certain amount. Now, can we explain why that is when we look at these two diagrams? Here are two liquids, same liquid in fact. One is just evaporating and one is boiling. Okay, so particles are escaping into the gas. Okay, particles are also escaping into the gas here. So what's the difference? What's the definition of a liquid that is boiling? Okay, well, here, if a bubble tries to form in this liquid, so if a liquid tries to evaporate not from the surface, but inside the liquid, what will happen to that bubble? Well, it will just get squashed by the atmospheric pressure, which if it were at sea level will be 1 atmosphere. Okay, here, these bubbles, in other words, the pressure of the vapor inside those bubbles must be big enough that these bubbles can grow and press out against this external pressure. So this must be equal to the outside pressure as soon as these bubbles start to form. Right? Now, here the vapor pressure must have been less than the external pressure. Here the vapor pressure has reached the external pressure. So we call a liquid, we say that when a liquid is boiling, we say that its vapor pressure is equal to the external pressure. Okay? The vapor pressure of, when the vapor pressure of a liquid is equal to the external pressure of a liquid, that's when the liquid starts to boil. Okay? And the boiling point of a liquid is quite simply the temperature at which that happens. So the boiling point is defined as the temperature at which the vapor pressure equals the external pressure. Okay? Now, some effects that can be explained using this idea. Liquids boil at much lower temperatures when the external pressure is lower. Remember from the previous slide, as the temperature increases, the vapor pressure increases. Okay? So if the external pressure falls, so if I go up Everest like I do every other Sunday, and the pressure is quite low, this external pressure is quite low, then my liquid will start to boil when the vapor pressure is quite low. In other words, at a lower temperature than usual. All right? So liquids will boil at lower temperatures if the external pressure is low. They'll boil at higher temperatures if the external pressure is high, because I have to get the vapor pressure higher to equal that external pressure, and that means a higher temperature, of course. Okay? Right. This bubble thing often quite confuses people a little bit, so check that you understand it, okay? And come and see me if you're having difficulties with it. I'll try and explain it to you in a slightly different way. Okay? Now, what's vapor pressure got to do with purity? All right, now you might remember from earlier, in an earlier film, that a solution, right, has a higher boiling point than the pure liquid, right? What does that mean? Well, that means that the vapor pressure of the substance, here the solution, won't reach atmospheric pressure until a higher temperature. Okay? So if I add impurities to a liquid, right, its boiling point will rise. We know that already. That means I have to get its vapor pressure up. I have to raise the temperature of the liquid higher to get its vapor pressure up to atmospheric pressure. That's what it means when we say it's got a higher boiling point. Okay, it means its vapor pressure equals atmospheric pressure at a higher temperature. All right. So if I have these two graphs, I can also see that at any particular temperature, the vapor pressure of the pure liquid is higher than that of the solution, okay? And this is what we were looking at earlier on the earlier graph, that if the boiling point of a liquid is lower, its vapor pressure is higher, okay? Now, good news, that's the last film of theory about kinetic theory, but bad news is, as you've seen, it's probably quite a long film, and there's lots and lots of points in it to note. All right, and some quite difficult ones to understand. Please take care to watch this one again until you understand it and until your notes make sense to you. It's no good if you go back to your notes on this film and you don't understand what they mean. Okay, now just to help you out, the last film, or hopefully to help you out, the last film that you'll watch, the sixth one, is a bit of practice of questions on this topic. So hopefully it will make some of the things that we've been talking about a bit clearer and give you an idea of what sort of things you're going to have to answer questions on.